Good evening, everyone. Can you hear me? Okay. So let's wait for maybe 3, 4 minutes for more people to join and then we can start. Meanwhile, you people can maybe fire up your Google Colabs. Can you confirm if you can see my screen, the Colab notebook? Okay, so in that case, let's proceed. Uh, what is it? Good. Yeah. Good evening, everyone. So, for people who are new here, my name is Buruj. I'm a fourth year PhD at IIT Delhi. I research graph machine learning, and I am your TA for the live sessions for this course. For people new here, we upload all of the recorded lectures on this YouTube playlist. So, in case you missed the session or you want to attend it later, you can view it here. In these sessions, we try to apply the concepts that we have learned in the lectures on in code you on publicly available data sets, and you don't have to take any screenshot, etc. Both the videos and the code is available on this GitHub repository, so you can carry along. The structure of these lectures, of these practice sessions, goes like this: that I give you a problem, I give you some time to solve it, around like 10 minutes or so. You can attempt it, you can use any online resource that you want, your lectures, any documentation, etc. And then I walk you through the solution on my side, and then we discuss any doubts that may have. Okay, so today's first question would be related to sampling that was covered in the last week, and then we'll build towards this week. Okay, so let me paste it. Let me know if the font is okay. Okay. Is it visible? Good enough? All right. So we are working with the Titanic data set. I'll give you the link for the same. By the way, if you see me looking this way, it's actually just a second screen to keep note of your chart. So let me give you the path. Okay. So this is the Titanic data set. If we load this. Okay, so you would notice that it essentially contains the passenger ID. Did they survive the crash or not? What was their class, like first class, second class, third class, their name, gender, age, etc., etc. So we want to work with this. Your first task is to implement a simple random sampling to select 100 passengers from this data set. In that 100 passengers, compare the survival rate to the original full population. That is, within your population, how many people survived on average compared to the full population, how many people survived. Repeat this random sampling 1000 times and create a histogram of the survival rates. That is, in my first sampling, this many survived, second sampling, this many survived, third sampling, this many survived. So you will get a list of your survivals. Try to plot that using a histogram to see what does the distribution look like. And finally, you would like to calculate the mean and standard error for this distribution of means that you have created. Okay. So it is 7:38. You can take, wait, it's 7:08. So you can take maybe till 7:20 to do this, and then we can carry on. So if you try to paste the link in your browser, remove the quotes on either side of the URL for the Titanic dataset, that is, like this. Should work. Any WhatsApp group where we can discuss our doubts only for students. I'm not aware of it. Maybe you can create one. In Jupyter Notebook, it's showing yes, you are not audible. Maybe try importing pandas first. Voice is not audible. Can you hear me? Okay. Yeah, as I said, I don't know about any WhatsApp groups. You can create one, I mean, between yourselves. I think it would be better if you just drop your email ID and ask people to mail you if they want to join the group, rather than pasting the link of the group itself. Yeah, so it would be a student group. I won't be in that group. It's just for your convenience if you want to create. Okay, so it's 7:46, 4 more minutes, and then we'll discuss. No, the screen isn't stuck. I haven't written anything. I'm waiting for you to solve. All right, I believe we can start. Just to confirm, you can see my screen, you can hear me clearly. Okay. So the question was to load the data set that we already have. We have a URL. You can, again, this is just a CSV file. If you try to open it, it looks something like this, a comma separated file. You can load it into a pandas data frame, and we see the data looks something like this. We want to implement a simple random sampling to select 100 passengers from this data set. So how do you do that? And suppose we even have that, what do we want to do with it? We want to compare the survival rate in the sample with the survival rate of the entire population. So we want the sample a population. We want to calculate the sample mean. We want to calculate the population mean, and we want to compare the two. So the first thing is to create a population. So we can say our sample is Titanic dot sample. We say that we want 100 passengers, and there is another thing called random state that I'll get into just now. So for now, let's say I'm passing it equal to 0. I'll tell you what this is. So if we just do this part and try to look at what we get, so this is a random sample. You would notice the indices are jumbled: 495, 648, 276. So it has randomly sampled all of them. And if I run this again, you would notice that these numbers do not change. But suppose I remove this part, random state equal to this, and now I run this. Now 226 is the first column. Now 25 is the first column. So what is this random state that is allowing us to repeat results? When you try to create randomness in a computer system, you can only achieve something called pseudo randomness. Okay, so suppose you ask a computer to generate random numbers. By its nature, a computer is deterministic. It cannot randomly throw numbers at you. So it does what is called pseudo randomness. So there is an algorithm that is responsible for creating numbers that look random. But that algorithm always needs a starting point, which is called a seed. So for example, when I pass random state equal to 0, this is my seed. If I pass a different seed, that becomes the starting point. If you know the starting point, then you can predict the numbers that it will generate, like the first number, the second number, the third number. So in this way, you are able to achieve pseudo randomness. That is, the numbers look random, but if a different person tries to run your code, he will get the same results. Okay, so that is why we are passing random state here, so that if you run this, you will probably get this thing. So this is sometimes dependent on the machine. That is, if I run it on my laptop and you run it on your laptop, this sometimes changes, sometimes it's independent of the machine. So it varies. But I mean, at least on the same machine, the random state will achieve the same results. So we have our sample. What do we want to do? We want to calculate the survival rate in our this thing. So we can say sample survival rate is equal to um, sample we have survived, and we can say mean. We can also say sample survival std is sample survive dot std. So this is one. We can do this again for the whole population. Maybe better to do this above. So we can say population survival rate is equal to population dot Titanic survived dot mean, and we can again say std, and then we can compare them. We can write population survival rate is this thing, and our sample survival rate is this thing. Okay, So we see that there is some difference between our population and this thing, and that is to be expected. If we run this again, nothing will happen. If we change the random state to something else, this can change like 0.39. It can again change to like 0.42. So this changes. But the population mean will not change. So you will also notice that we have used some wordy terms for our variables, and I would encourage that you do the same because it ensures that if someone else reads your code, they can understand what variable, I mean, each pertains to. So now that we have this, what have we done? We have implemented this, we have compared the this of this. Now we want to repeat this process 1000 times and create a distribution of these survival rates. So let's do that maybe in a different cell. We can delete this, delete this, delete this. Okay, so we want to simulate this thing 1000 times as said above. Maybe we can calculate this part here. We want to simulate this test. Each sample has size 100. This is again up to us. And since we want to create a distribution, let us maintain a list of these means. We'll save them here. Okay. So now we iterate for I in range, number of simulations. We can say that I'll create a new sample, which is essentially running this thing again. But this time we don't want to use a random state. Okay. Because it will essentially do the same thing repeatedly. So we get a sample, and then we can say survival rates dot append sample survived dot mean. If we just run this much and check what we get in the survival rates, you would notice that this is one giant thing of means. It will have 1000 means of our different population. Okay, so we have this part. Repeat the process 1000 times, and now we want to create a histogram out of this. Okay, so to create a histogram, we will use matplotlib. Let's say figure comma xc is equal to plt dot subplots. My figure should be of size 12 by 6. And what do we want to do? We want to create a histogram. So we can say ax dot hist, plot the survival rates, use 30 wins. I also want a edge color. And if we do fig dot show, we see something like this. Okay, you can also add a grid or something and maybe lighten these things up a bit, but this is essentially the main part. So to elaborate this thing, maybe we can also plot these things. That is, what was our sample mean, what was our population mean. So we can say that it would be better to do this. Still works. So we have our histogram. Let us create a marker for population mean. Let us create a marker for sample mean, for mean of sample means in fact. So the way you do it is you use a vertical line. So you want to say I create a vertical line at position this part, population survival rate. And if you just run this, you would notice there is this line, but it's not quite visible. So we can change the color. We can say make it red color. So you get essentially this line. You can make it more fancy by adding maybe the line style, label, etc., etc. But for now, Let's keep it simple. We'll say this is the population mean. We'll create another line. This will be for our sample rates dot mean. Sample rates is this thing, a mean of means. Okay. Survival rate, not sample rates. And this time, let's make it maybe green, and we can name it something else. Sample mean. Okay, so you would notice that they are almost the same thing, but the green line can vary if you, change this. And we can finally say ax dot legend, ax dot grid. So when you write ax dot legend, you would notice that we had passed these labels. That is, sample mean should be red colored and this should be this. So it can show you the same thing. For someone visualizing, it can say that the red line is signifying the population mean, the green line is signifying the this thing. So where have we reached? We have repeated the process 1000 times. We have created a histogram of our mean. So this histogram is essentially your mean of means. That is, most of your means are in this region. A few of your means were quite small. A few of your means were quite large. And that is essentially our histogram. The final part was to calculate the standard error between the two. So if we do that final part, we can print our sample distribution stats. We can print that our mean was this much. We can print that our standard error was this much. Then we can say that our theoretical standard error was this much. So let's fill in these values. We already have this thing. We have survival rates dot mean, and we want only 4 digits. For the standard error, you can say survival rates dot stt divided by np dot square root length of survival rates. And the final part is the theoretical thing, which should essentially be equal to, I think this is the theoretical part. Yeah, this should not be it. This is the normal thing. This should go here, and it should just be the population standard deviation. This part should be your sample standard, this thing. So if we print this, we see that our standard error is this much. We are quite a bit off. Survival rate mean, survival rate standard deviation. We have population standard deviation divided by the, oh, this is the wrong thing. It should be sample size. Yeah, now we are close. So 0.46, 0.48. So we have essentially covered all of these. Any questions related to this before we move ahead? You can unmute.
Yeah, if I'm audible.
Mhm.
So we counted, sorry, we counted
Could
the
you
mean
repeat?
for the, yeah, for this for the survived one. But
Mhm.
essentially, what we are counting in the data set is an count of one wherever applicable, right?
I could not hear the last part. So you said something about the mean and then.
So in the function in the code, you wrote mean,
Mhm.
right? Dot mean. But
Mhm.
essentially, we are counting just the number of one in the particular column of the survival.
Yes,
I mean, is
yes,
that
you can say
understanding
that.
right? Yeah,
Yeah, yeah, yeah. Essentially, these are zeros and ones, right? So if you just
right.
compute the mean, that is essentially the same thing.
Okay. So because I took count of one as in
That's the same
like
thing, yeah, yeah. And then
right.
you
But
divide.
how? Yeah. Do you see any like issue if it's a different type of data set? Like, will this be a better practice or the other way around?
I mean, of course, I mean, let's say your this thing was a string and we'd say yes
Hmm.
or no. In that case,
Right.
I mean, you would use a count, yeah.
Okay. Got it. So if we have to count a specific like name or say like a drug in that data set, so we will be using count, not the mean,
Hmm. You could use
right? So,
count, or you can also create a mask, like something like this. You could say, for example, your df, my particular column
hmm.
should be equal to, let's say, yes. So this now becomes your
Okay.
mask. Then you can say mask dot sum divided by length of mask. This becomes your average.
Hmm. Okay. Okay. This is helpful. Thank you.
Anyone else? Should we move on to the next one?
Oh, sir, will we get recording of this?
Yes, of course.
Where can we find its recording?
So you'll find it on this YouTube channel,
Data analytics using Python, yes.
this thing. You'll
Links are
see
there.
playlist here, and the code will be available here. If you, I mean, go to any of these lectures as well, you will find the links below them here too. So for example, you go to the description, you'll see the link to the code, the full playlist and the course website. Yeah. So you'll not lose anything. So in this session, the main part is that you want to practice. That is, some of these things may be easy, some of these things may be redundant, but the thing is, the more you do it, you develop muscle memory for that. So that's the goal of these sessions. That is, the things you have read, can you apply them in practice? Do you have the confidence to, I mean, do this in real life? Anybody else? Should we move on?
Sir,
Mhm.
please explain this third part that you are
Which part?
histogram this. I have not
This
understood.
is. Mhm.
Yes.
Yeah, so in this histogram is not the survival rate, that is how many people survived. The thing is, we were in our earlier case, for example, in this case, we took just one sample and we printed the average survival rate. That is, in our sample, 43% survived, and earlier on, 38% had survived in the full population. We want to see, suppose we sample randomly 1000 times, and every time we sample 100 people. Okay, you sample 1000 times, every time you sample 100 people, among those 100 people, how many survived on average? So this histogram says that in some of your I mean, those samples that you took, only 25% survived. In some of them, 50% survived. And in most of them, 35 to 40% survived. So essentially, this is that among your 1000 samples, this is how the average survival rate looks like when you randomly sample.
Thank you.
Borrowed just one quick request if you can accommodate. Uh,
Mhm.
the questionnaire that you sent like in the beginning of class, can you just make an word file of it so that we can just look at all the questions at one place?
Water.
Can I do what?
A document of all the questions. This so that we just have a question in one place for practice.
So for example, I mean, if you go to these notebooks, you should have everything. I think, for example, you have question one, question two, question three, question four. Do you want something else?
No, I think this will do.
Hmm?
This will do. Thank you.
Okay, okay. So in the notebooks, essentially what we are solving here, you will find it there. And once you open the Jupyter notebook, you can always just collapse these and you will get questions, questions, questions. Yeah. So you don't have to worry about, I mean, storing any of this. Just focus on solving this. I'll give you all of the material. You can always revise.
Sir,
Mhm.
please explain random state.
Random state. Okay. So I was saying that in a computer, if you ask it to generate, let's say 10 random numbers, if I ask a human, he can say maybe 10, 12, -1, 3. A computer cannot essentially do that. Can you hear me?
Yes.
Yeah. So a computer cannot do this thing like this, generating random numbers by itself. So you have to develop an algorithm, and by nature, an algorithm is deterministic. So how do you emulate this randomness? So this is called a pseudo-random algorithm. A pseudo-random algorithm generates these seemingly random numbers, but it needs a starting point, and then it follows a sequence. That is, I'll do this operation and give you this. It's essentially a complicated operation, and you don't know the because you don't know the algorithm, they look random to you. If you knew the algorithm, they are still non-random numbers. So the algorithm needs a starting point, which essentially is called the seed. This is your random state. So when you pass random state equal to 0, it is essentially passing seed equal to 0. In some libraries, you also do that. You say seed is equal to this thing. In some things, you can say this. For example, if you use NumPy, you can do np dot random dot seed is equal to 0. So this essentially sets the seed for NumPy library to be 0. And everything you do afterwards in NumPy, it follows the seed. Okay. So that is what we are doing with seed. We are setting that for this particular random experiment, if I rerun it, I want the same random numbers every time. You would notice that we did not do it here. When we sampled in this part, we did not set the random state to that number because it may generate the same things repeatedly. However, in a loop, this should not happen, but still. Does that make sense?
Yes.
Okay. So I think we should move to the next part. I'm muting you for the time being. So this was a random sample. Now we want to go for something called a stratified sample. You must have read this last week. So the thing is, you have this population of passengers. Some of them were first class passengers, some of them were second class passengers, some of them were third class passengers. Naturally, I mean, if you even go on a flight nowadays, there are very few first class passengers or business class passengers compared to the economy class. Okay. But when you randomly sample, you may disturb this split. Okay. So when you do a random sampling, the thing that you achieve is you want to maintain that proportion. That is, if 20% were first class, 5% were business class, and the rest were economy, within my sample, the same ratios should hold. That is 5% business class, 10% from the first class, and the remaining from the economy class. So we want to do the same thing. That is, rather than sampling randomly, can you first divide your data set into these three strata? Your first class, your second class, and your third class citizens. And rather than sampling randomly, do a stratified split where you pick 200 passengers from each of these. Okay. And finally, you have implement stratified random sampling to select proportional sample of. So when you say 200 samples, essentially 200 should be the full size. And within those 200 size, a portion should be for first class, a portion should be for second class, a portion should be for third class. Finally, compare the class distribution of your stratified sample with the original thing. That is, the class distribution means how many are first class, how many are second class. You want to compare this ratio. Am I actually meeting the ratio in the original thing? Then again, you want to compare this with a random sample. That is, how are you doing compared to the random sample? So try to do this. And it is 7:44. We can wait till 7:55 and then we can carry on. All right, it's 7:55. Let's start. So the problem is, as we said, stratified random sampling. We have a data set. We have three classes of people, first class, second class, third class. We want to sample in such a way that the proportion of these class distribution holds. So the first part would be to calculate, sort of to create the strata. We should know how many, like what ratio or maybe what percentage of data points to sample from each P class, passenger class. Maybe we can say what fraction. That would be better. Once we have this, then we can do a stratified sample. Essentially, what we are doing here is we have to create a new data set, create a new DF, and finally, maybe we can print the stats. Okay, so this is how we'll break our problem. So another thing to note is there are a total of 200. Our sample size should be 200. So let's note that our sample size is 200. We'll start with that. So to create the strata, we'll say that my class proportions are Titanic. It is called P class dot value underscore counts. If we print this, you would notice that there are two things. A, we are getting a count rather than a fraction. Okay, we don't need the count, we need a fraction. That is, this is the proportion in which I should do this. Another thing is they are not in the correct order, that is 3, then 1, then 2. So to fix this, we can say in value underscore counts, I want to normalize this. Now, if you print the same thing, you would notice that these are fractions. That is 50% of your population is third class, which is expected, and your first class is 25%, and your second class is 21% approximately. So we have our fractions, but the indexing is still a bit wrong. So the way you fix this is you say reset or sort underscore index. You get 1, 2, 3. First class is this much, second class is this much, third class is this much. So this is just a style thing. You don't have to do this, but I mean, just to know. So because we have these, we can now convert this into my, I mean, how many people should I sample from each class? So we can maybe place this here. How many to sample? In fact, even that isn't necessary, but still. So stratified sample sizes would be essentially my class proportions multiplied by this thing. That is 25% of 200 will go to first, these 20% of 200 will go to the second, and so on. So we just multiply this by our sample size. Okay, so we have this, and we can, because these are people, we don't want them to be fractions, we can round this. So if we print this part, we have stratified sample sizes. In our first class, we have 48 people. In our second class, we have 41 people. And our third class, we have 110 people. Again, we can try to cross-check whether we are doing it right. See, this doesn't seem right. 111, why is that? Oh, because this is just one number, sorry. So if you had a series, I mean, first class, I have a lot of them, then that would help in that case. In this case, you just have to divide by the count. Yeah, so it's essentially the same thing. So we have this thing. Now we want to create a new data frame in which we will sample 48 people from the first, 41 people from the second, and 110 people from the third. So if we break down this problem, we need to create an empty data frame. Then we will iterate over the passenger classes. Following that, we'll get the P class that we are working with. We should know how many people to sample in this P class. Once we have this, we can sample a new DF, and we will append this DF to the empty DF. Okay, so pretty simple. We have three classes. We will iterate over the classes. Once we have our class, we should know how many people to sample. We sample that many people from the data frame, which gives us a new data frame, and we append that data frame to our previous data frame. Appending essentially means you plug it in from the bottom in the rows. Okay, so and the next class comes, you append it again. So if we go on to do this, how do we create an empty data frame? We can say stratified sample is equal to pd dot data frame. It's empty, we don't pass anything. Then to iterate over the classes, we say for p class, in this case we know it's 1 2 3, otherwise you can do unique or something like Titanic dot p class dot unique. That's another way to do it. So we have our passenger class. We want to know our data, that is get data for this P class. We can say class data is Titanic, and I only want people whose P class is the current P class. Okay, so this is my class data. I want to work with this. How many people do we want for this? We say number of samples is just that we calculated earlier, this thing. My P class, this gives me how many samples to pick, and the remaining is pretty easy. We can say our class sample in this case is class underscore data. This is this particular thing. I want you to sample n samples from this. N is equal to n samples. And again, for pseudo randomness, we can pass a state. So normally, if you were doing this in NumPy, you would not have to pass this, I mean, random state every time. You would essentially define it at the top of your this thing, that is period.random state is this, and you run it. But sometimes what happens in Jupyter Notebooks is every cell has its own random state. That is why I'm passing it random state again and again. Normally, if you were running a Python script, it's just one file. You don't have to do it again and again. So we have our class sample, and then we just append, or it's also called concatenation. So we can say stratified sample is equal to pd dot concat. So just so you know what concatenation means, so suppose you have this um, data frame. Okay, so this is row 1, row 2, row 3, and you have another data frame which has, let's say, 2 rows. You want to sort of mix these two like this. That is, it should create one data frame where the rows from the second data frame go below the rows from the first data frame. This is called concatenation. You're concatenating along the row. You can also call it append or concat. Means the same thing. So we have this thing. What do we want to concatenate? In your concatenation, you pass a string and sorry, a list. And in your list, you say these are the things that I want to join. So initially I will pass the empty one, and we want to concatenate this guy, my class sample. Okay, so if we run this and now we print our stratified sample, you would notice we will get a new this thing. And now if we do the class dot value underscore counts, you would notice this, and maybe we should normalize, and we can again sort underscore index. If we compare this against the full thing, I think we deleted that. If we compare this against the full thing, that is Titanic, you would notice that they're pretty close, like 24242. This is also like in differing in the third digit. We have 20%, this is 20%, this is 55%, this is also 55%. So we have done a stratified split. That is, the proportions are the same. So what was the next step? You want to compare the class distribution in this. So we have done that part just here. The class distributions are pretty much the same. You can also plot this. And the other thing is calculate the mean fair for each sampling method and compare the population mean. So this essentially means that you want to create the mean underscore stratified is from my stratified sample. I take the P class and I get his mean. What did we miss? Yeah. Similarly, you can do this for a random sample. You can say Titanic dot sample. You sample a random set of people, and then you take their mean. So this will become your mean random. And then we have our mean population, which will just be the full thing. That is Titanic P class dot mean. And if we were to print these mean, mean random, in population, we get something like this. Okay, so this is 2.3, this is 2.3, and this is 2.19, the random sample. The random sample will of course change every time, but our other two are fixed. So this changes because we have not set a particular seed. So this is when you compare these. Again, you can also plot this. Maybe when I upload the notebook to the GitHub, I will add a plot for this. That is how do the, I mean, populations differ. Which method gives you a more representative sample? So this is for you to decide. I mean, think about it. I'll maybe also add the answer to this. This is especially useful when you are doing, let's say, machine learning. When you do, suppose, machine learning and you have a particular data set. Suppose you are working with this Titanic data set itself, and you want to split your data set into two parts, one for training the model and one for testing the model, okay? Or maybe validating the model. When you train the model, you want the training population to look similar to the full population because you are essentially sampling out a portion, right? That is why you create a stratified sample. That is, you respect the class imbalance. However, when you create a test data set, you don't want it to be imbalanced because there you want every class to get an equal opportunity. So there you create an equal split for the test set. So that's a different thing. That is, I mean, if you, I think would have noticed that is, suppose I ask you to take 100 from each, now it's a balanced set. So that you would use for a test set. Okay. So essentially, I believe we have covered all of stratified sampling. Any questions regarding this? Let me unmute you. Go ahead. Anything? No questions? Should we go ahead?
So don't understand label code.
Which one? Can you point it out? What did you not understand?
Stratified random sampling.
Yeah, so in stratified random sampling, in suppose you have a big data set, let's say 1 million points, and I ask you to sample out 100 points. If you do a random sample, you're essentially giving equal probability to all of your points. That is, you could pick any damn thing. Okay. However, if there are, let's say, particular sections in your training this, I mean, in your population, that is, some of them are first class, some of them are second class, some of them are third class, or suppose you have data from different countries. Let's say some people are Indian, some are American, some are Europeans. Okay. Now, it may happen that there are a lot more Indians compared to Europeans. Let's say Indians are 80%, but Europeans are only 20%. And if you were to do a random sample, then you are essentially giving Europeans the same priority as the Indian, right? But if you want to respect this population, that is, even when I sample, among those 1 million people, if I just sample 1,000 people, 80% of them should be Indians. You want to enforce this class ratio. That is when you use stratified sampling. In stratified sampling, you have to first identify what proportion should I pick from each class, and that part you pick randomly. That is, that 20% of Europeans, you will pick those 20% randomly among the Europeans, not overall. That is the essentially the idea of stratified sampling. Does that make it clear?
Yes, sir.
Anything else? Should we move ahead? Anything in the chat? Okay. So moving on, let me again mute you for the time being. So let us go to the third question. We actually have a total of 4 questions. We see if we have the time for the fourth one. When does this end? We started at 7, right? So we have time. Let's see. So this is a different data set compared to what we were doing right now. Let me give you the path before I explain what we are doing. So I pasted it in the chat, the essentially the code to import this thing. So you must have read about the central limit theorem in your lectures. We would like to verify it empirically. So what does the central limit theorem say? Central limit theorem says any distribution, no matter what it is, if you were to sample from it repeatedly, and if you take the mean of those samples, that distribution of means is always Gaussian. And if you standardize it, you achieve a standard normal distribution. This is the central limit theorem. So we would like to do this empirically. That is this actually true? So we load the video game sales data set. You would notice that is we have different games, Super Mario, Mario Kart, Pokemon, etc., etc. And the thing that we want to work with is the global sales. We want to examine the distribution of the full population. That is overall, what is the population of global sales? How many people make this much, this much, this much? The wealth distribution sort of. Okay. So once we have this overall distribution, let us now sample. We take a sample of size 5, then we take 10, then we take 30 samples, then we take 50 samples. Every time we take these samples, we always sample 500 games. Okay. So when I say n equal to 5, I'm essentially saying repeat this experiment 5 times. Each time sample 500 games. Calculate the mean of those 500 games in each of those n's, like n equal to 5, you will get 5 means. In n equal to 10, you will get 10 means, and so on. And then again, plot this histogram. Okay. Or you can just print it out. That is what is my mean and what is my standard deviation. If plot is difficult for you, you can just write it down. That is assuming it's normal. What is my mean? What is my standard distribution? And then we can compare, that is, as n grows, is our population going towards a Gaussian distribution or not? And if we standardize it, does it go to a standard normal? So I would like you to do that. Any questions about this before we start? Let me unmute you if you have any difficulty with the question. Is the question itself clear? All right, so I'll assume there are no questions. It is
Sir,
8:15.
can you
Yeah, any
explain
question?
again this
Yeah,
central limit theorem?
yeah. So the central limit theorem essentially says that you can have any distribution, that is, it can be a binomial distribution, a Poisson distribution, or even uniform, or I mean, just a random sample. If you just plot the histogram, for example, we had the histogram earlier. Did we plot anything? Yeah. So for this is already Gaussian, but still, if you have any type of distribution, it need not be Gaussian distribution. Suppose that distribution has, let's say, 10,000 points or so, or let's say 1 million point, 100,000 points. If you sample, let's say, 100 points once, you sample 100 points again, you sample 100 points again. So these are 3 samples. You compute the mean of this thing, you compute the mean of this thing, you compute the mean of this thing. So you sample thrice, you have 3 means. Suppose you sample many times.
தூக்கமே வரல இங்க படுத்திருந்தேன் திரும்ப இங்கன பாய வச்சு இங்க பாய வச்சு படுத்திருந்தேன் திரும்ப மாமா கிட்ட கொண்டு பட்டேன் திரும்ப இங்கன வந்து பட்டேன் இங்க தலைய வச்சு பட்டேன் அங்க தலைய வச்சு பட்டேன்
Mm. So suppose you sample many times. As many times you sample, you get that many means. If you were to create a distribution of these means, and if you were to plot it, let's say, or you just compute the mean and STD, you would notice that this distribution is a Gaussian distribution, no matter what distribution you started out with. So this initial distribution, that this can be anything, need not be Gaussian. But if you sample many times from it and you look at the distribution of its means, not the distribution itself, like this is not Gaussian, that the distribution of the means is Gaussian. This is the central limit theorem. So we want to verify this empirically over this particular data set. Is that clear, Siddharth? I think you asked it.
Yes, sir.
Hmm. Please dying.
Sir, can you move the screen up?
Yes.
Um, no.
So this n equal to 5, this is not how many games you are sampling. Remember, this is the number of times you are sampling. And every time you are sampling 500. So don't confuse these two. And again, if plotting is hard, you can just print the mean and standard deviation for now. I mean, that essentially won't give you the shape, but I mean, I'll show you how to plot it because I'm assuming that maybe you are not accustomed to plotting multiple things at once. So for people saying that there is an error, I think you should be able to access it. Just don't include these quotes at the end. So this happens every lecture. This should just start with an R, end with a V. No quotes. If you use this path, in fact, if you just paste what I'm giving you, it should work. All right, so let's get started. The first part says examine the distribution of your global sales for the entire population. So essentially, we want to create a histogram for the global sales. How do we do this? We have our sales. We only want to work with the global sales and we want to plot it. When we plot it, we want to say that I want a histogram. Again, if it's a histogram, please use the black edge color to distinguish between the bars. I want the figure size to be 12 by 6 and a title and some labels would be very good. We can say that this is the population distribution of global sales. My X is my global sales in millions. My Y is the frequency. And what else? I think that should be good. We can add a grid. We can add a transparency to our grid and we can say reality.show. Okay, so you would notice that this is similar to what we had, I think, in the first or second lecture. That is, we have just one bar and essentially this is wasted space. So, but that is actually not true. What's happening here is that majority of our data lies in this bin essentially, but there is still data here, but it is too small compared to this thing. That is, if you want to visualize both of them at the same time, you only see this part. So there is data here, but it's minuscule. So how do you visualize something like this? You use something called a power log, sorry, a log scale. Here you can say that I want the log scale to be true. So if we compare these two, you would notice that here the bins are 0, 20, 40, 60, 80. Here too, 0, 20, 40, 60, 80. But the Y is different. The frequency is 2000, 4000, 6000. But here it's in powers of 10. Okay, so every time it doubles. Like it is multiplied by an order of 10, not double essentially. So you start with 1, then you go to 10, 100, 1000, 10,000, and so on. And now you can see a distribution. But you can also notice that it is definitely not a Gaussian distribution. Okay, we can make it better by maybe also specifying that I need more bins. So it has automatically decided for a particular set of bins. We can say, let's say 50 bins. Again, we can do this here as well. Yeah. So this is our distribution. If we don't use the log scale, there's our distribution if we do use the log scale. Now coming to the next part, it says take samples of size n equal to 5, 10, 30, 50. We can maybe use different, maybe these are too small. For each sample size, we want to draw 500 samples. From those 500 samples, we want to take the mean and then we want to plot the distribution. So rather than plotting, let us just first calculate the mean and then we can update it for plotting. Okay. So our sample sizes are, according to the question, 10, 20, 30, and 50. I think these may end up being too small. Let's maybe take bigger ones. Let's take 10, 50, 100, and we can take 1000. Okay. We want to do this 500 times. That is, I think this is the opposite, right? Did I explain it the other way for you? Draw 500 samples, take sample size of that. Oh, I did it the other way. So we want to simulate this 500 times and we want to sample this many people every time. Yeah. So once we have this, what do we want to do? We want to iterate over the sample sizes. While iterating, we would like to draw the sample and calculate its mean. Okay. And we could also store the sample stats for later use. Okay, because we would like to plot it maybe or maybe examine it. So we can maybe use a dictionary to save it. We can say our results will be stored in a dictionary, and we can maybe have a separate dictionary to store the means. So let's go about this. We can say for n in sample sizes, what do we want to do? Our current sample means is an empty list. We'll populate this. We can say for I in range, we want to do this many times. For I in range this much, please sample please sample endpoints. N equals n. I mean, you could pass with or without replacement. It's the same thing. Usually, when you try the central limit theorem, you do it with replacement. So you have this, and we can say that for this particular sample, we got a particular mean. So we can say sample means dot append sample dot mean. So this list that we maintain, we append the particular thing for this. So every time we run the simulation, we are storing the mean in this one. So because we're doing it 500 times, this list for this particular n will store 500 means. Okay. So once we have this, what do? We can say mean underscore dictionary n is equal to sample means. In fact, we should maybe first uh, turn it into a numpy array. It's easier to work with. Okay, so we have our mean dictionary. In this, we have stored it for visualizing it later. And then we can maybe store a few other things. We can say that I want to save the results for this particular n. And here in this particular dictionary, I want to save another dictionary. I would like to store the mean to be something. I would like the theoretical SE to be something. I would like the actual SE, and I can also store the data here. I mean, we could just store this thing here rather than doing this thing. This is just for our simplicity. We can maybe use either one of these later. Okay. So if we get the mean, we already have this. We have sample we have sample dot mean, sample underscore means dot mean. We have our theoretical SE, which is my VG sales, global sales or standard distribution divided by NP dot square root of n. That is how many data points are there. My actual is the standard deviation of this thing, that is sample underscore means dot std, and the data is my sample mean. So if we run it, what do we have in results? So we have our keys 10, 50, 100, and 1000. Suppose we try to look at 10. What do we have? You will notice that we have the theoretical SC to be 0.49. Our actual SC that we computed came out to be 0.43. We have also stored the means for all of our data points. Okay. So we could, in a sense, just do away with this. We're not using this. So we have our data. Now we would like to see if this distribution, you see this data, is this Gaussian? We have a mean, we have a standard deviation, but can you plot it essentially? So rather than doing it maybe in multiple subplots, maybe show you one by one. I mean, that will maybe confuse you if I plot them simultaneously. So we have PLT dot subplots. We would like the figure to be maybe 12 by 6. We have our axes dot histogram, and what do we want to plot the histogram for? We'll say results, and suppose for 10 we would like to do this. Please use, how many bins did we use earlier? 50 bins, yeah, 50 bins. I would love an edge color of black, and anything else. Edge color bins, we can have this. So this is our population distribution of means. Mean of global scales, and we have frequency. And if we do pic.show, got multiple x's, what did we pass? Oh, that's singular. Got multiple values for argument x. It's a single value. Oh, wait, it's because of this. Hmm. Hmm. So we have this particular distribution. You would notice compared to the original thing that looks something like this. This is relatively Gaussian. Of course, it is tail heavy. Let's do the same thing for what are the other sample sizes? 10, 50, 100, 1000. So let's do it for, let's say, 100. We copy this thing here. We get 100. You would notice that it has improved relative to last time. It's more Gaussian. If we do this again for 500, what was the other one? 10, 50, 100, 1000. Okay, 1000. So it's even better. Okay, so we notice that the distribution of means becomes more and more Gaussian as we increase n. So the central limit theorem essentially says that when your n goes to infinity, that is, it becomes a very large number, you get a perfectly Gaussian distribution. You could also plot a Gaussian distribution on top of this using the mean and standard distribution here. So suppose we do x is equal to np dot linspace. I think this will just confuse you. Yeah. So essentially we get these standard distributions and we can essentially prove, I mean, visually, that is, we are improving the Gaussian distribution as we take more and more steps towards this direction. Again, because we are doing this in separate plots, this comes out to be very visually unpleasing. So what you want to do is you want to create multiple axes. You can say that if you look at the subplots, each is number of rows, number of columns. Suppose I ask it that I want 4 rows and just one column. Are you asking something? So what am I essentially doing here? So when you do this, figure is equal to this thing. Suppose I do this in a separate cell. If I print the axes, you would notice that this creates four separate plots for you because you supplied number of rows is equal to 4. So 1, 2, 3, and 4. Of course, you want more height. So let's say 12 by 12. So you get something like this. Now you can index each of these axes when you plot something. So what I'm doing here is when I want to plot it for n equal to 10, I will use axis 0. When I want to plot in the second plot, I will use x is equal to 1. So I am indexing the same way you index anything in Python. Okay. So what are we doing here? We are enumerating. Enumerating essentially means doing two things at once. A, you want to get the points inside the sample size. That is, for example, my first I will get 10, then I will get 50, then I will get 100. Along with this, I would also like to have the index. That is, give me 10 and the index of 10, give me 50 and the index of 50, 100 and the index of 100. So in this case, this is enumerate gives me both of these things at once. I get the index and I get the value. So I can do plot this thing in this particular index and use this particular n. The rest of it remains the same, right? Everything else is the same. So if we try to plot it like this, we get all of these distributions in a single thing. If we just delete the remaining ones as we don't need them anymore, and we can increase the columns size, we get all of these distribution in a single setting, right? The y distributions are the same. You can also set them to be share x is equal to true. You would notice that if you use a single this thing, as your n increases, your population is concentrating around your mean and it's becoming more and more Gaussian and very little is found elsewhere. For more aesthetics, I mean, you can just drop this part and then it can show you the full thing like this. You could also plot, I mean, the PDF for this thing, but I think that will just confuse you. Maybe I will add it to the notebook, and if you want to look at it, you can use that. So essentially in that case, you have to create a sequence of x points. You want to use the PDF of a normal distribution to plot the points, and then you want to plot the curve on top of this. So I think that will just confuse you if we do this right now. We can maybe do this later. Any questions in this part? I mean, in this, what we did just now. So this is clear? Okay, so I'll assume that there are no questions. Not able to add a cell, yeah. So coming to the last question, let me explain it. It's 9:15, so I don't think we'll have the time for it, but I'll add the solution in the notebook and you can first try it yourself and then look at it here. So this is a different data set again. This is related to this week confidence intervals. So there is a different data set called the student performance data set. It looks something like this. This is the data for a particular class. We have the gender, we have bachelor's, etc., etc. But mainly we have these scores: math score, reading score, writing score, etc., etc. We would like to calculate the point estimate for the math scores. That is essentially the average of the point scores for the entire population. Can we sample out, let's say, a sample out of this data frame and calculate its point estimate? So that will give us another mean. We would like to construct a 95% confidence interval around this. So this you have studied in your lectures. That is, how do you do this? You, for a 95% interval, assuming that is again, because you are sampling multiple times, again, you can use all this z-score, etc., etc. So you have to compute those alphas. Then you have to go 1 minus alpha on the other side. That is, on the left side of the PDF, you have alpha. On the right side of the PDF, you have alpha. So because this is 95%, your alpha is essentially 5%. So you want to cut off 2.5% on one side and 2.5% on the other side of the PDF. Then you want to compute the z-score on the left side and the z-score on the right side, and that will essentially give you your confidence intervals. Once you have your confidence intervals, you would like to repeat that process 50 times and check how many times does my confidence interval contain my actual mean. And finally, you would like to say what additional information is this confidence interval giving me on top of that. Okay, so let me paste this part in the chat, and I'll upload the solution to this when I upload the notebook. Okay. So for this, you first need to know how to do this part. Okay. So you may have to review your lectures. That is, how do you compute the confidence interval? Because it's not straightforward, this part. Okay. Any questions for this thing? Otherwise, we can end the meeting. Let me maybe paste the question as well, if you'd like to try it out later. All right. So let me stop sharing. Let me stop recording.
Sir, there is any WhatsApp group here to discuss these things?
So there is an